The Foundations of Geometry by David Hilbert.
Chapter 6, Pascal's Theorem. Section 33, the commutative law of multiplication for a non-Archimedean number system. Theorem 39, for a non-Archimedean number system, the commutative law of multiplication is not a necessary consequence of the remaining laws of operation. That is to say, there exists a system of numbers possessing the properties 1 through 11, 13 through 16 mentioned in section 13, but for which the commutative law 12 of multiplication is not valid. A Desarguian number system, in the sense of section 28, is such a system. Proof. Let small t be a parameter and capital T any expression containing a finite or infinite number of terms, say of the form capital T is equal to r sub 0 t to the n plus r sub 1 t to the n plus 1 plus r sub 2 times t to the n plus 2 plus r sub 3 times t to the n plus 3 plus ... where r sub 0 is not equal to 0, r sub 1, r sub 2, ... are arbitrary rational numbers, and n is an arbitrary integral rational number less than equal greater than 0. Moreover, let small s be another parameter and capital S any expression having a finite or infinite number of terms, say of the form capital S is equal to s to the m times capital T sub 0 plus s to the m plus 1 times capital T sub 1 plus s to the m plus 2 times capital T sub 2 plus ... where capital T sub 0 is not equal to 0, capital T sub 1, capital T sub 2, ... denote arbitrary expressions of the form T, and m is again an arbitrary integral rational number less than equal greater than 0. We will regard the totality of all of the expressions of the form S as a complex number system omega st, for which we assume the following laws of operation, namely, we will operate with S and T according to the laws 7 through 11 of section 13 as with parameters, while in place of rule 12 we will apply the formula Ts is equal to 2st, equation 13. If now capital S prime and capital S double prime are any two expressions of the form capital S, say capital S prime is equal to s to the m prime times capital T sub 0 prime plus s to the m prime plus 1 times capital T sub 1 prime plus s to the m prime plus 2 times capital T sub 2 prime plus ... Capital S double prime equals s to the m double prime times capital T sub 0 double prime plus s to the m double prime plus 1 times capital T sub 1 double prime plus s to the m double prime plus 2 times capital T sub 2 double prime plus ... Then by combination we can evidently form a new expression capital S prime plus capital S double prime, which is of the form capital S and is, moreover, uniquely determined. This expression, capital S prime plus capital S double prime, is called the sum of the numbers represented by capital S prime and capital S double prime. By the multiplication of these two expressions, capital S prime and capital S double prime, term by term, we obtain another expression of the form capital S prime capital S double prime is equal to s to the m prime times capital T sub 0 prime times s to the m double prime times capital T sub 0 double prime plus the quantity s to the m prime times capital T sub 0 prime times s to the m double prime plus 1 times capital T sub 1 double prime minus s to the m prime plus 1 times capital T sub 1 prime times s to the m double prime times capital T sub 0 double prime, plus the quantity s to the m prime times capital T sub 0 prime times s to the m double prime plus 2 times capital T sub 2 double prime plus s to the m prime plus 1 times capital T sub 1 prime times s to the m double prime plus 1 times capital T sub 1 double prime plus s to the m prime plus 2 times capital T sub 2 prime times s to the m double prime times capital T sub 0 double prime n paren plus ... This expression, by the aid of Formula 1, is evidently a definite single-valued expression of the form capital S, and we call it the product of the numbers represented by capital S prime and capital S double prime. This method of calculation shows at once the validity of the laws 1 through 5 given in section 13 for calculating with numbers. The validity of law 6 of that section is also not difficult to establish. To this end, let us assume that S prime is equal to S to the M prime times capital T sub 0 prime plus S to the M prime plus 1 times capital T sub 1 prime plus S to the M prime plus 2 times capital T sub 2 prime plus ... And S triple prime is equal to S to the M triple prime times capital T sub 0 triple prime plus S to the M triple prime plus 1 times capital T sub 1 triple prime plus S to the M triple prime plus 2 times capital T sub 2 triple prime ... Capital S prime and capital S triple prime are two expressions of the form capital S, and let us suppose further that the coefficients R sub 0 prime of T sub 0 prime is different from 0. By equating the like powers of small s in the two members of the equation, capital S prime times capital S double prime is equal to capital S triple prime, we find, first of all, in a definite manner an integral number, m double prime, as exponent, and then such a succession of expressions, capital T sub 0 double prime, capital T sub 1 double prime, capital T sub 2 double prime ... And that by the aid of Formula 1, the expression capital S double prime equal to S to the M double prime times capital T sub 0 double prime plus S to the M double prime plus 1 times capital T sub 1 double prime plus S to the M double prime plus 2 times capital T sub 2 double prime ... satisfies our equation 2, and with this our theorem is established. In order, finally, to render possible an order of sequence of the numbers of our system, omega of st, we make the following conventions. Let a number of this system be called greater or less than 0 according as in the expression capital S, which represents it, the first coefficient R sub 0 of T sub 0 is greater or less than 0. Given any two numbers, A and B, of the complex number system under consideration, we say that A is less than B or A is greater than B according as we have A minus B less than 0 or greater than 0. It is seen immediately that these conventions, the laws 13 through 16 of section 13, are valid. That is to say, omega of st is a de Sargian number system, see section 28. As equation 1 shows, law 12 of section 13 is not fulfilled by our complex number system, and consequently the validity of theorem 39 is fully established. In conformity with theorem 38, Archimedes' theorem, theorem 17 of section 13, does not hold for the number system omega st, which we have just constructed. We wish also to call attention to the fact that the number system omega st, as well as systems omega and omega t we made use of in section 9 and section 12 respectively, contains only an enumerable set of numbers.
The Foundations of Geometry by David Hilbert. The material contained in the following translation was given in substance by Professor Hilbert as a course of lectures on Euclidean geometry at the University of Göttingen during the winter semester of 1898 and 1899. It was translated by E. J. Townsend, Ph.D., University of Illinois. The text was downloaded from Project Gutenberg with the following notice: this ebook is for the use of anyone, anywhere in the United States and most other parts of the world at no cost and with almost no restrictions whatsoever. Read by Jim Renholt. Programming and illustrations by Jim Renholt. 2019. Portrait of David Hilbert by Rita Ray Renholt. Thank you for listening.